So this tutorial explains how to use the free fall velocity function that we created in the previous tutorials and create a script to simulate results for different values and solve the problem that was at hand. So now if we go back to our original question, we are trying to find out the velocity at 10 seconds after the drop, and also we are trying to find when does the object attains terminal velocity. So for this purpose we will write a script that will help us go about finding these values. So open a new file, and let's call this script for simulating velocity of free fall. And let's define some variables. Let's say t0, which is our initial condition, is 0, and v0, which is our initial velocity, is 0. And now based on this information we are going to find what is the velocity from numerical method, and make sure that you spell it correctly, otherwise you will get an error. Given the velocity 0 at t0, we want to find the next velocity at 1 second. So let's call that t1, and let's call this v1. So right here we'll say t1 is equal to 1. And so our next velocity depends upon our previous velocity. And in a similar manner, we can also find the v1 sub a, which is the actual velocity, by using velocity actual at t1. So as you can see, this will give me two values that I can use now to find out what's the difference. So actually let's put a subscript here, v1n, and then let's call this v1a. That might be a little bit better nomenclature for this. And now I can just copy paste this and run it, or I can save it and then run it. So let's call this velocity sim, which means velocity simulation, or you can call it velocity run, which also means the same thing. Okay, so we save it and then we run it, and as you can see, I made it's saying undefined function, which means I made a spelling mistake in giving the name of the function, and I missed a t. And let's run this again, and now I made a mistake in calling this function velocity actual whereas it is velocity analytical. And now we run it, and it ran fine, and we can see it updated all of these values in the workspace. We can see that the numerical value is 9.8 and the actual value is 8.67. Now of course this is not what we are interested in. We are interested in at 10 seconds. So we'll replace t1 to be 10. So what we are saying that the initial velocity is 0, and now what is the velocity at 10 seconds? And we run the same code and we look at the values, how they're updated. The numerical value is telling us that it will reach 98 meters per second, whereas the actual value is telling us that it's 35. So we can quickly see what the error will be. v1a minus v1n, and the error is minus 62 meters per second. So our numerical method is overestimating these values. Now let's break this into two steps. So instead of jumping to 10 seconds, we will create an intermediate step. We'll say we will compute first at 5 seconds, and then after that we will use the value at the 5-second as the initial value for the next step. So t2 is equal to 10, and so v2n is equal to velocity, and of course you can cut paste the top line. I will type everything for now. So here our initial condition is the previous time step, so I want to use v1 numerical at t1 and find out the value at t2, and similarly I can find my actual v2, which is velocity analytical at t2. Okay, now because as you can see the alignment has changed a little bit, so in order to make it a little bit more readable better, I will just add some spaces so that it is better aligned. So now if I run it, I will also see the values at 5-second and 10-second. Now if we go here, we can see that at 5 seconds, the velocity, computed numerical velocity is 49, whereas the actual velocity is 27. So in this case, what ends up happening is that the numerical implementation has overshot. It started from 0 at v0, and then it went to 49, and from there it says, oh wait a minute, I am way past my actual value, so it went back. And it's in numerical methods, a lot of times over the course of time some of these things converge to, or try to converge to, the actual solution. Now we'll do the further breakdown of this into 1-second increment, or maybe 2-second. That might make the step easy first. So we do 2-second, and then 4-second, and then we'll add some more lines for 6, 8, and 10. Copy pasted the code, but it's very logical that at each step the computation for the numerical part depends upon the output of the previous step. Okay, now let's run this, and now we can see the output at various steps. And now you can see again, it started at velocity 0, then it jumps to 19, 29, 34, 36, and then here it again seems to have overshot the actual value. So it's after this step, if we go one step further, it is going to try to come back towards 35. And this process will continue to change as we keep increasing the step size. So the next we're going to do a step size of 1 second, but to do that, instead of going through these stepwise processes, we'll create a for loop, which is the topic of the next tutorial.